Hello? Where's everybody at? It's like I'm teaching to an empty classroom. Let me see here. Let me look around the corner here. Oh, there you are, sitting at home, watching YouTube. Hold on a second. Okay, that's better. All right, so let's get into our lesson for today in our journey through calculus. Today we're going to be talking about the idea of implicit differentiation. And so far we have specifically focused on taking derivatives of functions. And that's all good and that's all fine. But what happens if we want to determine the slope of a graph or a curve that isn't a function? Think like the equation of a circle. Remember, the equation of a circle is x minus h squared plus y minus k squared equals r squared. So you can see in that equation, let me go ahead and write that down for you, x minus h squared plus y minus k squared equals r squared. You can see that this is not explicitly written. Remember, explicitly means that y is isolated. Now we can isolate y. It's possible to do that. We would get y equals plus or minus radical r squared minus x minus h squared and then plus k all on the outside. So we can explicitly write y by itself, but we'd have to include the plus or minus to represent the entire circle. If we didn't, if we just had that would imply that we're dealing with only the top half of the circle, and if we put a negative out front, that's dealing with the bottom half of the circle. Now, with that said, what if that's not our goal? What if we don't want to focus on just one part of the circle, but we want to focus on the entire circle? Or some functions that are really disgusting. I mean, you may get something that looks like this, right? You may get spirals and things like that on your curves. How do we take derivatives of those types of equations? Can't call them functions because they're not, but equations nonetheless. Okay, and that's kind of the goal of implicit differentiation. That's what it helps us do. So our objective is to be able to determine the derivative of, well, I wrote a function here where y, the dependent variable, isn't isolated. Okay, essentially that would imply that if you can do that, then you can take the derivative of any equation that isn't necessarily a function. Okay, so before we do that, let's go back a second and talk about the difference between explicit formulas versus implicit formulas. So explicit formulas are where the dependent variable is isolated. In other words, we have that input-output thing, right? So you have the x that you're inputting and it goes through the machine, and then out comes the y value, the output. And so we get y equals whatever this produces. Explicit, y equals something, okay? An example of this is y equals 3x squared minus 5, or f of x equals 4 cosecant of x squared plus 1. These are all explicitly written because it specifically talks about what y equals, okay? So for implicit differentiation, we don't have to have the dependent variable isolated. It can just be part of the rest of the equation. So for example, y squared equals x. We don't have y by itself here. Now we could get y by itself, but that actually might cause more problems than it's worth. Or 3xy equals 17. Or x squared minus xy plus y squared equals 7. This deals with a lot of the different forms of conic sections, which I know that we haven't really talked about in prior math classes, because that has been something that's kind of gone by the wayside in terms of mathematical curriculum over the last few years, but these are dealing with conic sections like a hyperbola or an ellipse, things along that nature. Okay, so with that said, let's go back and talk about some very important things in making sure we understand the difference between these things. Okay, so if I were to ask you what is the derivative of each of these things, what's the derivative of x versus the derivative of y? What's the derivative of 2x versus the derivative of 2y? Or the derivative of x squared versus the derivative of y squared. Well, here's the thing. You would have to know what variable you're taking the derivative in respect to. Normally, we take the derivative in respect to x, which implies x is the variable, and then y normally is the function. So if we were to, or the output value. So if we were to treat it that way, where y is the output, where it was the dependent variable, it depended on what x is, let's go ahead and take those derivatives. Well, what's the derivative of x in respect to x? Well, the derivative of x in respect to x would be 1. What's the derivative of 2x in respect to x? Well, the derivative would be 2. And then the derivative of x squared in respect to x would be 2x. We'd use the power rule. So that's all great. Now here, what if we took the derivative of y? If we took the derivative of y in respect to y, then what we're saying is that y is the variable, and so therefore this is just 1. Same thing if we took the derivative in respect to x of just x. And then if we took the derivative in respect to y of 2y, we would just get 2. And then the same thing here, we get 2y. But what happens if we treat y as the dependent variable, or the function, if you would? So that means the variable is x. What if I took the derivative of y in respect to x? What is that derivative? Well, we call that y prime. The derivative of y in respect to x is y prime. And you can see it here. If I have f of x, as an example, if I have f of x equal x squared, and I say take the derivative, that implies algebraically that you have to take the derivative of both sides. So what's the derivative of this function? Well, it would be f prime of x equals 2x, because we took the derivative of f of x, which is f prime. The derivative of, if we just replace the f of x with y, the derivative of y is y prime, and the derivative of x squared is 2x. We are taking the derivative in respect to x, okay? So that's pretty straightforward. The derivative of y is y prime, okay? Now, here's where maybe we get a little bit tricky. What is the derivative of 2y? Well, if we use our same rules that we've used in the past, right? We're taking the derivative in respect to y. What rule would we apply here? Well, we would take the constant multiple out, and we would just multiply it by the derivative of what's there. So what's the derivative of y? The derivative of y is y prime. So the derivative of 2y is 2y prime, because y is a function, so the derivative of a function is y prime. Okay? Here, what's the derivative of y squared? Well, even more in depth, we want to see this as the chain rule. What's the derivative of something squared? Well, it's 2 times something. And then we have to multiply it by the derivative of that something. So we have to multiply it by the derivative of y, which is y prime. So the derivative of y squared is 2y times y prime. Now you might be asking, why didn't you use the chain rule up here? Well, I could have. I could have very easily used the chain rule. What is the inner function? Well, if I were to circle the inner function here with a marker that actually works, that might be a good idea. If I were to circle the inner function here, x, well, what's the derivative of something squared? It's 2 times that something, in this case it's x, and then times the derivative of that something. Well, what's the derivative of x? The derivative of x is 1. But that just simplifies to 2x anyways. So here, if this is my inner function, because it is a function, it's in terms of y, or the y is the dependent variable, then we'd say 2 times the something, and then times, to the first power, times the derivative of that something. Well, what's the derivative of y? It's y prime. Derivative of y is y prime. So that is kind of the foundation of implicit differentiation. We need to know what the difference is between taking the derivative in respect to x of x versus the derivative in respect to x of y, right? Versus the derivative in respect to y of y. If this is my variable, this is telling me y is the variable, so the derivative of this is 1. This is telling me x is a variable, so I'm treating y as a function, so the derivative of this is y prime, and then x is my variable here, so I'm treating this as a variable, so the derivative of x is just 1. Okay, so hopefully you kind of get a good grasp of what that means. All right, let's go ahead and go on to the next thing and hopefully get some practice in here. Okay. Be very careful with this. Students tend to have a hard time with the y squared, especially the 2y and the y squared. Here's what students want to do with the 2y. I guess I should talk about this for a second. They want to say, oh, the derivative of that is going to be 2y times y prime. Not making the connection that this is a constant multiple, okay? It's a constant multiple, so ignore it. The derivative of y is y prime. Now multiply it by the constant, which is 2, so it's 2y prime. I'm just pointing that out because that's, for whatever reason, that's a common mistake that students make over time, okay? So again, we use the chain rule on this one. The derivative outside times the derivative of y times the derivative inside. All right, so let's go ahead and take a look at an example of what this looks like when we don't have an explicit equation. Well, let's take a look. Here we got y squared equals x. And we're looking for dy dx. Well, we've got to read what this is saying. It's saying take the derivative, we want the derivative of y in respect to x, which means x is my input, x is my variable, and y we are treating as our output, our function, if you would. So I want to take the derivative of this. So what is the derivative of y squared? Well, that's 2y times y prime. And then what's the derivative of x? The derivative of x is 1. And so we can isolate y prime by saying y prime equals 1 over 2y. And so we have dy dx, because remember, y prime just means dy dx. So that's a great example. Derivatives follow the same algebraic rule as anything else. Whatever you do to one side, you have to do to the other. Now, maybe you can recognize how to isolate y so that you can take this explicitly. Well, I would take the square root of both sides, so I'd end up with plus or minus rad x. And then I would have to take the derivative, or I'd have to break this apart into two separate functions because this is dealing with the top half of that parabola, and then this one's dealing with the bottom half, making the entire parabola. The reason we write it in implicit form is so that we don't have to break it apart. This just represents the slope, okay? So let's go ahead and take a look here. If I were to take the derivative of this, we'd get y prime equals 1/2 x to the negative 1/2. And then here we get y prime equals negative 1/2 x to the negative 1/2. And so simplifying this, we end up with y prime equals 1 over 2 rad x. And then here we get y prime equals negative 1 over 2 rad x. Now, there's a range restriction here because this is dealing with the top half of the parabola. So therefore, we would say that this is true for y is greater than 0. Okay? And this is true for y is less than 0. Okay? Now, some of you might be going, well, how does that relate to what you were talking about? Well, it's pretty simple. If y were to be replaced with what it is equivalent to, watch what happens. We end up with y prime equals 1 over 2 times y. So 1 over 2 times positive or negative rad x, which is exactly what we have here, depending on which part of the parabola we're talking about, okay, the upper part or the lower part. So we don't want to write it explicitly because we want something that represents all things, okay? So this is our derivative there, okay? All right, so again, differentiate both sides. So you end up with 2y times y prime equals 1, and then we isolate y prime. We end up with 1 over 2y. Now, we should leave it in the form that it asks for. Dy dx is 1 over 2y, and that would probably be a better way of expressing it. All right, you should probably go ahead and pause the video and try these problems. And when you think you got it, or this problem, I should say, when you think you got it, come back and compare to my work to see how you did. For this practice problem, we have x squared plus y squared equals 25. And we are looking for the slope the slope of the tangent line when, or at, at 3, -4 and at 3, 4. Interesting. Interesting. Think about what this is doing. Graphically, I'm asking you for the slope of the tangent line at 3, -4 and 3, +4, which implies I'm looking for a slope at the same x value but different y values, meaning that this isn't a function. So we can't express this explicitly in a simple way to be able to find these slopes. So we go about it implicitly. Now you should recognize that x squared plus y squared is actually a circle, and it's centered at the origin with a radius of 5. Okay? So we have a circle, something along this line, and I'm asking you to find the slope at 3, 4 at this point and 3, -4 this point. So we're trying to find the slope of the tangent line here and here. Okay? Now you'll notice that these are actually mirrors of each other. They're reflections of each other. So that would imply that the slopes should just be opposites to each other. So let's go ahead and do the work and see what we come up with. Well, remember we're taking the derivative in respect to x. So the derivative of x squared is 2x. The derivative of y squared is 2y times y prime. And we put a plus sign there, the sum rule. Same things apply. Now what's the derivative of 25? The derivative of 25 is 0 because it's a constant. And then from here we can isolate y prime. We'll go ahead and subtract the 2x. We got 2y times y prime equals -2x. And then we'll divide by the 2y, so we get y prime equals -2x over 2y. And so y prime equals -x over y. So I have now my derivative expression written as a relationship between x and y, which means you need to know what x value and what y value you're plugging in to find the slope. And that makes sense graphically, because if I were to just tell you what's the slope when x equals 3, if you knew what the graph looks like, you would say, well, wait a minute, there's 2 points when x equals 3, so what's he talking about? And that's why you need a y value to figure out these slopes. Okay? So the way I'd express this is I would say y prime evaluated at the point 3, -4, so we got like a subscript here, is equal to negative parentheses 3 over -4, which is 3 over 4. And so we can see at the coordinate 3, -4, we have a positive slope, so that kind of makes sense. The slope at that point is 3/4. And then if we look at this other one, we would say y prime evaluated at 3, 4 would be equal to, the equation is -x, so it's -3 over y, which in this case is just 4. So we end up with -3 over 4. Okay? And you can see again at 3, 4, we see a slope of -3 over 4. Now, I will say that this is just coincidence that these coordinates produced a slope with those same two values. Okay? It just worked out that way, and the reason I had to do it is because it's hard to find specific coordinates on a circle, nice whole number coordinates. I'd have to deal with decimals for most points on that circle. Okay? So that is a great example of implicit differentiation, and the idea that you're going to need an x and a y value to determine a derivative, because in these types of equations, or these types of graphs, we have multiple y values for a single x value. And that can be, there could be more than 2. There could be 4 or 5 or an infinite number. Okay? All right, so again, taking the derivative there, notice the notation that I use here. I took the derivative in respect to x on both sides. So the derivative in respect to x is 2x plus 2y times y prime equals 0. And then we isolate y prime, and we have our derivative expression. And then we can plug in our coordinates and get our slopes out. Okay, so that wraps up that problem. Let's go ahead and take a look at another practice problem here. Let's see what you can do on your own. Again, pause the video, see what you got, come back and compare what you got to what I got, and let's see how much you know. Okay. All right, for the first problem here, we've got 2y equals x squared plus sine of y, and we're looking for dy dx. So again, we're looking for the derivative of y in respect to x. So that means y is an output, x is an input. So treat y as a function and treat x as the variable. Okay, so what is the derivative of 2y? Well, take the constant out. What's the derivative of y? It's y prime. And then multiply it by the constant, so we have 2y prime equals, what's the derivative of x squared? Well, that's 2x, that's easy. Now, what's the derivative of sine of y? What's the derivative of sine of y? Well, you have to treat this as a chain rule, as a composition of functions, because the inside thing is in itself a function. So treat it like the chain rule, or use the chain rule. What's the derivative of sine of something? Well, that would be the cosine of something. And then we have to multiply it by the derivative of the inside. So the derivative of the inside is y prime. Okay, I'm going to put parentheses around that y, so I know I'm only taking the cosine of that. And then our goal from here is to solve for y prime, get y prime by itself. What is y prime equal to? So how could we go about doing this? Well, we're going to have to get all the y primes over on one side. So it might look something like this: 2y prime minus cosine of y times y prime equals 2x. And then we're going to factor out a y prime because both of those have that. So we get y prime times 2 minus cosine of y equals 2x. And then we can get y prime by itself just by dividing by that entire parenthesis. So we end up with y prime equals 2x over 2 minus cosine of y. And then again, we can rewrite that as dy dx equals 2x over 2 minus cosine of y. So that is my derivative of y in respect to x. Now, you may have done something slightly different. You may have moved the y primes over to this side and the x over to the other. So you would have gotten negative 2x equals cosine of y times y prime minus 2y prime. And then we would have factored the y primes there. So y prime times cosine of y minus 2 equals negative 2x. And then we'll divide by the parentheses now. So we end up with negative 2x over cosine of y minus 2 equals y prime. But you can see that the difference between these is just a multiplying this by negative 1 over negative 1, you would end up with the same thing. So if I multiply this by negative 1 over negative 1, that becomes 2x. That becomes negative cosine of y. That becomes positive 2, and so we're left with this. The goal is to try and reduce the amount of negative signs, and so this would be the better form of writing that. All right, for the next problem, it says, what is the equation of the tangent line and the normal line of x squared minus xy plus y squared equals 7 at the point negative 1, 2? So you may know what this function looks like, and that's great if you do. But if you don't, you can still answer the question that's being presented here. We have x squared minus xy plus y squared equals 7. And we're looking for the equation of the tangent line and the normal line at negative 1, 2. Negative 1, 2, we want the tangent line and the normal line. Well, in order to find the tangent line and the normal line, you need two things. You need a point and you need a slope. We already have the point, so that's nice. We just need the slope now. So to find the slope, we got to take the derivative. So the derivative of x squared is 2x. And again, going back to this idea of the chain rule, and it's always a good idea to think chain rule in everything you do. The derivative of x squared, well, treat x as the inside function, as my lights go out. Okay. Treat x as an inside function, so you take the derivative outside, which is 2 times something, and then times the derivative of that something. The derivative of x is 1. So we could write this as times 1, but it's still just 2x. Okay? It's just a good idea to think of the chain rule as you go through here. Now, on this one, you should recognize that this is a product of two things. we're going to go ahead and identify the negative x as the first thing and the y as the second thing. So what's the derivative of the first thing? The derivative of negative x is negative 1 times the second thing, so times y, plus the derivative of the second thing, which is y prime, times the first thing, so times negative x. So that's the product rule there. And then the derivative of y squared, again, treat the variable, if you would, the dependent variable, as a function, so or as a inside of a composition. So that would be plus 2 times something, 2y, times the derivative of that something, and the derivative of y is y prime. And then take the derivative of the other side, which is just 0. So now we have this kind of complex equation. Let's see if we can simplify this a little bit. We end up with 2x minus y times y prime. Sorry, that's not correct. 2x minus y minus xy prime plus 2y times y prime equals 0. And then we want to get all the y primes over on one side and everything else on the other. So I'm going to go ahead and move the 2x and the negative y over to the other side. So I have negative x y prime plus 2y times y prime equals y minus 2x. Add y to both sides, subtract 2x from both sides. Then I notice that I have a common factor of y prime there. So I'll go ahead and factor that out, and I end up with negative x plus 2y left over. And then to get y prime by itself, we would say y prime equals y minus 2x over negative x plus 2y. And so there I have the equation that gives me the derivative of that equation up there. From there, we're going to go ahead and plug in that point to get my slope. So we would say y prime evaluated at negative 1 comma 2 is going to be equal to, so we got to plug in y is 2, minus 2 times x, which is negative 1, all over negative x, so it's negative times negative 1, plus 2 times y, so 2 times 2. And so that simplifies to 2 plus 2 over 1 plus 4, so that'd be 4/5. So that is y prime evaluated at negative 1 comma 2, and that's enough now to figure out the equation of my tangent line and my normal line. So for my tangent line, I've got y minus 2 equals, my slope is 4/5, times x plus 1. So that is my tangent line there. And then for my normal line, remember, the only thing we have to do, we want to keep the point the same. We just want to make the slope so it's perpendicular. So it's going to be y minus 2 equals negative 5 over 4 times x plus 1. So that's the equation of my normal line. Let's go ahead and make sure I am correct on that problem there. And so we end up with y minus 2x over negative x plus 2y, exactly what I said. And our tangent line is going to be correct. So we're good there. Okay. So hopefully you're getting an idea of this implicit differentiation stuff. Remember to take the derivative in respect to x, which means you're treating y as a function. Okay. So you have to apply the chain rule. You have to think about the chain rule. Let's do one more problem. Let's do our exit problem here and see if you guys can do this on your own without my help. So here we are looking for the slope of the curve of this equation, of this graph. We have x plus 2 squared plus y plus 3 squared equals 25. And we are looking for the slope of the curve at 1 comma negative 7. Well, you should have already recognized that this is a circle again. It's got a radius of 5, and it has a center point of negative 2 comma negative 3. Now, that's not really important to answering this question, but it does give context to what we're actually trying to do. So I want to take the derivative of this. Well, I see a composition here. So the derivative of x plus 2 squared, well, treat the parenthesis as an inside function. That would be 2 times x plus 2 to the first. and then times the derivative of the inside. The derivative of x plus 2 is just 1, so I'm going to write that down, times 1. I know it doesn't change anything, but it's good habit to just write it down, because when we get to this guy, it's going to remind us to keep doing that. So again, we have an inside function. In this case, our composition has a y plus 3 on the inside. Now throw that marker away. So y plus 3 on the inside, so our derivative there is going to be 2 times y plus 3 to the first, and then times the derivative of the inside, which is going to be times y prime. The derivative of y is y prime. The derivative of 3 is 0, so y prime. Notice the difference here. The derivative of x is 1. The derivative of y is y prime. We can apply the chain rule in both cases, and we should. And then the derivative of 25 is 0. Now, we can go through a long process of distributing and all that stuff. That's just going to be a mess. Y prime is pretty simple to solve. We can just subtract this over to the other side, so we end up with 2 times y plus 3 times y prime equals negative 2 times x plus 2. And then we can divide all of this, so we get y prime equals negative 2 times x plus 2 over 2 times y plus 3. We can see that those 2's reduce on the outside there, so we end up with negative x plus 2 over y plus 3. If you wanted to, you could distribute the negative in, but that's not what the question was asking for. It did not say what is y prime. It said what is the slope of the tangent line, the slope of the curve at this point. So all we need to do now is plug in 1 comma negative 7 into that. So we end up with negative 1 plus 2 over negative 7 plus 3. And so we end up with negative 3 on top, negative 4 on the bottom. So again, we have a slope of 3 over 4. Okay, that is our final answer. Now, what I could have done is I didn't necessarily have to isolate y prime first. I could have just taken my derivative equation here. This equation has y prime in it, and that's what I wanted. I wanted the slope of the curve at this point. So I could have just plugged in 1 to x and negative 7 to y and simplified this and isolated y prime where there's only numbers left over. That might have been simpler arithmetic because it didn't specifically say find y prime, the y prime equation. But it's good practice to do this anyways. All right, with that said, that is the end of today's lesson. Let's make sure that I am correct here before I have you go along your way. We are correct. Notice I did it slightly different there. I did distribute the 2's here, and then I didn't reduce it, but still that wasn't the question. The question is, what is a slope? So hopefully you have a good idea of implicit differentiation and the idea of taking the derivative in respect to x when you're given y, right? Because the derivative of y is y prime if it's in respect to x. If I want the derivative of y in respect to y, then it would be 1. All right, if you have any questions, comment below. And I really cannot wait until we get to be back in person and teaching live. I'll talk to you all later.